Okay. Hello everyone. Hello everyone. Again, my name is Julián, whichever is easier. I've been recently appointed assistant professor here, and I work on information retrieval evaluation. And so I'm going to be talking about evaluation, of course, and hopefully you can see that a lot of the stuff that I'm going to talk about actually relates to recommender systems. It's going to be the same problems that I'm going to be talking about. So hopefully this will be useful to you. And since I'm in a recommender systems meetup, here's a new task for you. Recommend pictures for the first slide of a presentation of this building that don't look ugly, because I have a really hard time trying to find a picture of the building. So anyway, this is a stochastic simulation for evaluation research. And I'm going to start with Richard Feynman. There was this famous lecture he gave in the 60s in Cornell University. Probably you saw it. And what he said was, well, he was speaking about the scientific method and how we come up with laws and theories in science. And what he said is, if it disagrees with the experiment, then it's wrong. It doesn't matter, doesn't make any difference how beautiful your guess is, it doesn't matter how smart you are, or what your name is. If it doesn't agree with the experiment, it's wrong. That's all there is to it. And if we tweak Feynman's words a little bit to our advantage, what he said basically is that scientific progress depends on our ability to run experiments and the phenomena of interest that we want to study from the experiments. And so that actually means two things. Output data from those experiments to draw our conclusions from, right? And in many cases, especially in computer science, input data to the processes that we want to study. So for example, input data to a recommender system, input data to a classifier, input data to a search engine, like documents, images, all that, right? And so all the time, we're going to be needing data. And the question is, where do those data come from, right? You can guess it. I'm going to say simulation. So let's talk about information retrieval or something called the Cranfield paradigm, which is the name someone gave, I think it was Ali Borges who gave the name, to how we evaluate systems in information retrieval. So let's talk about the information retrieval use case. We have a system, a search engine, a collection of documents that we want to index, and we have a user. Of course, this is XKCD users. The user has some kind of information need, like I want to know what's the weather going to be tomorrow in Delft. This is also called sometimes the topic. So a user has a topic that wants to find information about and poses some query from that information need. The query is the actual text that you type into the search box. You give that to the query, the system gives you a set of results, the user goes to the results back and forth, sees, and many times you see yourself reformulating the query for the same information need. You go to the system again, the system gives a set of results, and you go back and forth, back and forth. So this is the basic use case, the traditional use case of information retrieval, right? So there are two recurrent questions all the time in information retrieval research. One is, I have my system, and I want to know how good the system is, right? Then we'll see what does good mean, as Michael was saying before. And then the other question is, I have a system A, a system B, usually a baseline, and I want to know which one is better, right? Those are the two questions that we are all the time asking ourselves in information retrieval, machine learning, recommender systems, etc. And so the thing is, we want to know which system is better, how good my system is over the population of users, over the population of topics, over the populations of documents, over all documents, all users, all possible questions that a user may ask the system. And there are many different questions that we may ask. But in the end, as we said before, I call it user experience. We're interested in somehow measuring the user experience, how the user interacts with the system. So for instance, you can think of time to complete the task, idle time, success rate, frustration, ease of learning. There are many different things that you may want to measure about your system and the user interacting with the system. And so those distributions describe the user experience, and that is what we want to know. For an arbitrary user with an arbitrary information need, what can I expect from my system, right? That's what we want to know. Now, I usually like to pose these kind of questions like in a formula. So we got a user measure, something that we want to know, as a function of the documents, the topic, the user, and the system. Those are the things, among some other things, that are going to decide what the user measure is going to be like, right? So our goal is the distribution of that user measure, but unfortunately it's impossible to calculate, right? Because there are possibly infinitely many questions, users, documents, so you can't just have all of them together and measure, right? So as usual in science, we have to estimate it, right? And so our measurement becomes an estimate with some degree of random error. So how do you measure these things? What is a good way of measuring how your system behaves, how the users interact with your system? One would say, well, you just get a bunch of users, have them sit in front of the computer, start using the system, and then implicitly or explicitly measure whatever it is that we want to measure, right? Can you think of a better way of doing it? I mean, you are actually having users posing questions, you see the users using your system, and that's the best way you can do it. But of course, it comes with a cost, a high cost. You have problems with representativeness of documents, the users, the topics, etc. Anytime you work with people, you have problems with ethics, privacy, a lot of things that you don't want to get into. And the two main points are these two here. It's hard to replicate the experiment when you have actual users doing something for you. It's very complicated to replicate an experiment, and it's just plain impossible to reproduce results. And that's what we want to have in science, right? We want to have it something that it's easy to replicate and that it's possible to reproduce. And if you have the actual users, boy, you're in trouble, right? So what we do, or what Cleveland did back in the 50s, was get a hopefully good sample of documents, of topics, and just fix it. Have it fixed so that everybody uses the same samples, right? So doing that, it promotes reproducibility and reduces the variability that we have in this course, because that is fixed. If we get something that is good, a good sample, let's fix it and use it. That's why we do it. But of course, we can't fix the users. You can't have the same users here and then 2 weeks now in San Francisco running some experiment, and then in Tokyo, and then here in Delft. You can't have the same users, right? So what we do is simulate them. And if you think about it, this ground field style evaluation, the data set evaluation that we used to carry out, is just a simulation. We remove the users from the equation, but we still have some user component into the whole evaluation process to simulate the users. And in fact, we have two components. A static component, you can think of the judgments, the annotations that you have in the ground truth. That static information that is supposed to be the same across users, and mark my words, it's supposed to be the same. And then a dynamic component, which is the effectiveness measure. Like you use precision, recall, average precision, NDCG, whatnot, right? And so those effectiveness measures are actually have behind them user models that model how the user interacts with the search, with the results of the system. And so by doing this, we remove all sources of variability in the experiment except for the systems. And that's great, because in the equation that we had before, that the user measure is a function of the documents, topics, etc., we don't have that anymore. We've come to a place where the user measure, it's something that only depends on the system in my experiment. And that's something that's great, because that means there are not any more factors interacting with my experiment, and I can get the same data set, run it somewhere else, and get the same results. So this is what we want to have. This is why we do things the way we do them. I think I went one back. Yeah. So the test collections is a control set of documents, topic judgments, served across the research, and combined with effectiveness measures. And I think they are the most important research and evaluation in information retrieval in general, because they make experiments inexpensive. Once you have the data set or the collection, you just run your system, run the numbers, and that's it. It has no cost. Of course, making the collection is expensive, but once you have it, you just run experiments one over again, right? So the good thing is that research is systematic. This is why we have test collections, because research is systematic and we can reproduce and replicate easily, right? And so in some way, the ground field style evaluation, how we do evaluations, they are simulation. It's a deterministic simulation, usually, but it's a simulation. We're simulating how the user interacts with the system. And all we do, all the decisions we have into making the evaluation are just going towards having good models of user behavior. When are we talking about that? So it provides us with the output data, the data that we need to decide what systems are better and how my system is, right? Of course, they have many assumptions. Michael went through a lot of them before. We're going to see some more. And so the thing is that this simulation works as long as it's valid and is reliable. As long as the simulation is realistic, you can say, as long as we are actually measuring something useful, something meaningful from the experiment, something like the interaction of the user, the browsing of the results, what utility the user gets from the documents, how the user goes from one document to the other, how accumulates the utility from the documents, and as long as the random error, because of the sample of documents, topics, etc., is minimized, right? So that's what we want to have in the evaluation, something reliable and something valid. Now let's see. So again, in the real world, we have actual users with information lists, documents, etc. If we do live observation, we can do that, and that's when I give you the actual numbers that you want to have. But because of several reasons, we abstract the user and have these two components that actually run a simulation in the ground field way, right? I don't know if you agree with this. Let's say that you do, and we move forward. By the way, if you want to ask anything, any question or any point, just let me know. So throughout the years, and I'd say especially 15 years or so, 20 years, we've been trying to just build better models. There's a lot of people saying we have to get away from ground field, we have to just ditch it and get something new, do living labs, for instance, or new evaluation frameworks to evaluate our systems. And I personally think that's a mistake, because we are forgetting about why we're doing this way in the first place. And so we're trying to build better models of browsing behavior, better models into the effectiveness measures. How we go from the topic to the query, just that basic step from going to what you want to know and what you give the system as a query. Simulations into how users go through sessions of queries, one query after another, and how the user accumulates some utility throughout the session. Simulation about the contents, the queries, the documents, the judgments, and even efficiency. We're using simulation to do all sorts of stuff, trying to improve how we evaluate ground field. And so just as an example, something that is really basic, but it hasn't been around for a long time. It's something like this. Let's say that the user expects the first result, with certain probability goes to the next one, and the next one, and the next one, the next one, and at some point the user stops. It's just pretty basic, right? But we've been doing this since 2008, I think. And so this is pretty new. And all the time we're doing like simulations as, or we're building our measures as expectations over the ranked list of documents, expectations over users, expectations over different things. We're trying to make it everything probabilistic in some way and trying to do better simulations. Then we go to something like this. The user formulates a query, goes to the first snippet, then with certain probability clicks on the document, reads it, judges the relevant, and then decide whether to go through several snippets or not. At some point, stop the session and finish. Again, it seems like, well, yeah, of course, that's how a user works, but we've been doing this for just a few years. It's just better ways of simulating the users. And so the two worlds of information retrieval, as I say, on the one side, we have information retrieval people trying to solve information retrieval systems, right? Problems. So they develop systems that solve retrieval problems, and they have to evaluate these systems to decide which one is better. And so they need use case data like we saw there. They need documents, they need users, they need topics, judgments, etc. to make good decisions about their research. But there's also information retrieval evaluation, and that's people like me who don't build those systems, but develop the methods to evaluate those systems. And so what we evaluate is the evaluation methods. What measures you use? How do you make the judgments? How do you collect documents? How do you collect users? Those kind of things. And so we need system evaluation data. The input data to me, an evaluation guy, is the output data that you produce. And so this is the key to the problem. This is where the mismatch is going to be, you're going to see now. And so let's go back to the reliability problem, right? So again, the test collection is just a sample from a larger, possibly infinite population of documents, user, judgments, etc. And so if we conclude that a system A is better than a baseline B, how confident can you be? Have you ever wondered this? How confident can you be? How much can you trust that simple statement? After all, that's why we try with different collections, right? Because with one collection you get that result, with another collection you get the opposite result. So which one is right? And so this all has to do with the mean score that you observe, the mean performance score that you observe with a collection is just an estimate from an observable true mean score on the populations of users, documents, topics, etc. So you want to know how close those things are together, right? This is what we want to know, but it's impossible, right? So this is basic estimation problem, right? It depends mainly on the size of the collections. The more topics you have, the better. The more documents you have, the better. The more judgments, the more users, the more of everything you have, the better, because that means your sample is better, right? And if there's one thing that we know in information retrieval is that the largest problem is the number of topics. We need a lot more topics than we have. And so a collection may be too small to trust. and that's just a simple fact. There are collections that are too small to trust. In all of information retrieval, multimedia, recommender system, machine learning, there are just data sets that are too small to trust. But there's also something as a data set that is too large. And I find it astonishing that not many people think about this. And they're building a new data set, and it's like, how much time we have? How much money we have? Let's just do it. Maybe you're not doing it the wrong way. Or you're doing it the wrong way, sorry. Maybe you're putting resources where you shouldn't. Have you thought about having multiple annotations from different users? Have you thought about the allocation of users to annotations or topics or judgments? I mean, there are a lot of design decisions that you have to make into making a collection. And really, people just say, well, let's make it larger. Larger is better, right? So there are two scenarios of interest here. One is you have an existing collection that is given to you as a PhD student, for instance. You have the collection, and then you wonder, well, how accurate are my results? So let's think like this. You have your collection, your scores, that's X, and you have the true scores. That's what you want to know. And so there are different ways of measuring how close those things are together. And because we in information retrieval like to be weird people, we have come up with many different ways of measuring just that, how close we are to the true values. We're going to see some of them. So that's one scenario. You have your collection, you have your results. How much can you trust them? What's the accuracy of your results? In the second scenario, however, you're building a new collection. So you're starting from scratch, you start adding topics, and you get data, more topics, start annotating, more topics. The thing keeps growing and growing and growing. So the question is, when should I stop? Right? When is good enough? Right? Or is it going to be like too expensive to have something that is good enough and I can just stop because I'm not going to make it? And so in the second scenario, you're worried about design, not about actual scores, but how many topics, how large should my collection be, right? So that it's good enough. And so we can think about the reliability of the experiment of the collection in terms of the expected accuracy that it will bring to us. What is the expected accuracy of a collection of that size as we were measuring before, right? When is it good enough? And so there are like two schools of measurement in information retrieval. One is the statistical, and the other one is the ad hoc or database. You have different names for them, depending on who you ask. And let's take a quick look at how we do this in information retrieval, or how people should do it, right? So one of the ad hoc measures is the rank correlation. It's based on the notion of a swap between systems. So let's say that we have two systems that are ordered like this in your results. According to your collection, this is the order. But according to the truth, it's actually the opposite, or like this, check, right? And so this is called a swap, a discordance. This is saying that the top system is better than the other one, but it's actually reversed, right? So if you take this over all pairs of systems, there's something called the Kendall-Tau correlation, which actually measures that. How many pairs are concordant, how many pairs are discordant? Of course, you want to have all of the pairs concordant, meaning the results that you get, the ranking of systems, is the same as the true ranking of systems that you want to know, right? And because in information retrieval we like to pay attention a lot to the things that are at the top of the list, there was something called AP correlation, that is something like following the same idea, the tau correlation, but pays more attention towards the top. So of course, you want to have the two top systems right. Maybe you don't care about the two bottom systems to be wrong, to have a swap in there, but you want the top systems to be in the correct order, right? So there are different ways of taking that into account. One of them is the AP correlation. And so in general, you want to have that correlation to be 1, to have your results just match what they are supposed to be, right? Another way of looking at it is called sensitivity. This is one of the really old ways of looking at this. And the idea is, what is the threshold delta such that if the observed difference between two systems is larger than delta, then we expect them to be swapped only 5% of the times. You see the point? So you want that measure, that delta to be close to 0, meaning that you can trust results that are really tiny, that even the slightest difference between two systems you can trust to be right. Right? So you want that delta to be small. And of course, we can express that delta in absolute terms, like a plus 0.06, or in relative terms, like a 3% improvement. If they tell me that anything beyond 3% has less than 5 probability of being wrong, then that's good, okay? And then we get into the statistical side of things, which I enjoy a lot more. And what we usually do is study effectiveness as a random effects model. And so what we do is partition the scores in this way. So this is, I don't know, the pointer is working? No, right? There's no pointer. I'm not sure you want that. Okay. So this is the score of this system on this topic, right? And we partition it as the mean score of all the systems on all topics, something called the system effect, the topic effect, and the residual. And the thing here is that system effects and topic effects are defined in terms of the mean score. So basically what this is saying is, if this system effect is positive, that means that system is better than the average. If it's negative, that means the system is worse than the average. How much positive, how much negative, then that means how much better than the average, how much worse than the average. And the same goes for the queries, or for the topic, sorry. If there is a topic with a large effect, then that means that it's an easy topic. It's easier than the rest because the systems are getting a larger score on that, right? So we usually employ a model like this, or something similar to it, right? And the important factor here is that each of those components have an associated called variance component, right? How much variability is because of each of those components that we have. So the idea basically is this. If this is the data that you have, we have here the systems, right? The mean scores of the systems. Then the best situation is one in which all systems are far away from each other, right? That means that we have a large variability because of the systems. So in this case, it's going to be easy to decide whether this one is worse than this one because they are far away from each other, right? However, that's not something that you can change in your collection. The systems are what they are. You can't change them. They are where they are. One thing that you can do here is increase the number of queries. And so if you are in that situation and you increase the number of queries, what happens is that those distributions get narrower, we get better estimations. And so in the end, it's going to be easier to find the difference between those two here because they already overlap, right? So this is more or less the intuition behind all this. Here, with just a few queries, they overlap a lot, so we are not really sure which one is better. But in here, they barely overlap, so we can make more reliable statements about this, right? So this is the idea, and there is something called generalizability theory, which includes different ways of measuring how much we can trust our results based on this intuition that we have. And the idea comes from classical test theory. I'm just going to skip over it. But the thing is that we use typically two. The raw square is one that tells us about the stability of the relative differences between systems. And the phi score is one that tells us about the absolute scores of the systems, right? So depending on which one is the matter to you, then you use one or another. And we want those to be close to 1. If they're going towards 1, that means your results are reliable. So this is a statistical way of looking into the problem of reliability in information retrieval, right? The other one is hypothesis testing. Oh my. One way of looking at it is if you have, for instance, an F-test, to compare many different systems, like your null hypothesis is going to be one system is the same as the other, the same as all the rest, then you can see reliability as the power of that test. If that test is likely to give me a significant result, then that's good, because that means I can trust my results somehow, right? If my collection doesn't have a high power, that means I can't trust the results. So this is another way of looking at it, right? All the boring stuff that leads to this. Did you get the catch in all this, in all I've been speaking about? There's one huge detail that is important here. Well, all the time I've been talking about the true scores, but we don't know what they are. That's what we want to know in evaluation, right? I'm all the time comparing to the true scores, correlation with the truth, right? Or the true scores of the systems in those distributions that we saw. But we don't know that. That's actually what we want to know in evaluation, right? So all the time I'm just wasting your time here, just speaking about something that we don't know, right? So when we speak about the accuracy of a collection according to the truth, or the expected accuracy of a number of topics according to the truth, well, I'm sorry, we can't do it. We can't compute that. The best we can do is, again, estimate it. So we are going to estimate something about the estimates, so to speak, right? And so there are different ways of estimating, for instance, the correlation between my results and the truth. There are different ways of estimating my rho square or the phi square between my results and something from the truth, right? So we don't know the truth, and that's the basic problem. That's the fundamental problem that we have in reliability research, that we don't know the truth. We don't know what the hell we're doing because we don't know what to compare to. That's where simulation is going to come in at some point. And so one way of estimating the ad hoc measures is what they call Speedhouse. And the idea is really simple. You don't need to read it. So you have a set of topics, and you split them in two. Or per se, you get 5 from one side and 5 from another. And you're just going to assume that one of those is the truth. And so you compute the tau correlation there, for instance, right? Then you repeat randomly another 5, and compute the same. Then you go 10 and 10 and compute. 15 and 15 and compute. 20 and 20 and compute. Up to the maximum of what you have divided by 2, right? So that gives you with a whole lot of points. The thing is that you interpolate those points and extrapolate to the number of topics that you want to know, right? So let me give you an example here. For instance, we have a collection here with 50 topics, so the best we can do is up to 25. And we are all the time just picking 2 subsets here. One subset, another subset, measure the correlation. One subset, measure the correlation all the time. And then you extrapolate. Now the problem is, what model do you use to extrapolate? In fact, we have those 3 models that you can find in the literature. Absolutely no basis for using one or another. So just pick whichever looks better, right? And in fact here, I could say that the blue and the red ones are looking better, right? The green one is going like off. We're going to see that's interesting. The green one is the one that works the best. And here is another example with the sensitivity. Just get all your data points and extrapolate to whatever size you want to see. So if I have a collection with 50 topics, how do I estimate the correlation with the truth? Well, I keep doing this, and then I extrapolate to 50, and that's what you get. That's your estimate of how well your collection reflects the truth. In the statistical side, we go with analysis of variance, or versions thereof. And I'm going to skip the details and just, we do analysis of variance to estimate each of those variance components, the system, the topic, etc. And in the end, we plug those estimates into different formula, and we get our estimates. And so the problem is, let's set aside for the moment which measure you prefer. You prefer correlation, you prefer tau correlation, you prefer sensitivity, absolute, relative, F-scores, whatever. Let's set aside that for a moment. Actually, there is a lot of research, mine included, saying that the current collections that we have in TREC, for instance, are too small, are ridiculously small. And there are some other papers saying we need hundreds of queries, we need even thousands of queries in some cases. In this particular case, we ran a study with more than 40 test collections for TREC from 1995, I think, to 2012. More than 40 collections measuring this and saying, hey, how well are we doing? How much can we trust our results from every year in TREC? And it actually doesn't look very good, because we have an estimate of the correlation of 0.7, and there's another thing that's for sure in information retrieval is that we want to have a correlation of 0.9. And what we have is 0.7. There is that magical number of 0.9 that came from a paper in 1998. Everybody wants to have 0.9, but that's what we have, 0.7. That's a lot less. And in terms of the raw score, for instance, we aim to something like 0.95, something like that. So on average, we are bad, right? And the point is that there are collections that are way, way, way smaller than they should be. You can't trust anything from those collections. And you have the numbers. This collection, don't trust. Okay? And so, wait a minute. Can we really trust that number? You see that I'm going to different abstraction levels here. Can we really trust that 0.7? Can we really trust that 0.88? I mean, after all, we are estimating these things. So I'm estimating something about your estimates. Are my estimates good? Maybe I'm telling you that your collections are too small, but maybe I'm biased. Maybe I'm telling you all the time that your correlation is smaller than it actually is. Maybe that's the case. Or maybe I'm telling you that your collection is better than it actually is, because I'm biased. I'm just like that. And so we can't know because we don't know the truth. So we go again to this fundamental problem. We don't know the truth, so how the hell we know how well we are doing? So just to give you a sense, each of those points is a different collection from TREC. Well, a different split of those ways that I told you about splitting the collection into. And for instance, here we have the tau correlation, one way of measuring, and you see the huge variability there is. There is not a single thin line going there like this is how we measure. There's a huge variability. That means we basically know nothing about how to measure these things. We don't know. We don't know how to measure them because there you go, right? Actually, let's go to the generalizability theory part. All this is based on the existing data that you have. A question is how sensitive are my results to the initial data that I have, right? And this is specifically important when you're building a collection. You have 5 topics, you run your systems, oh, this is more or less what we have, 50, right? Maybe you have 10 systems, 5 topics. What can you do from that, right? What this plot is showing is for a different number of systems, initial systems in your data set, in your existing data, then depending on what 10, 20, 14, etc. systems you get, this is the variability that you get in your scores. So that means if, for instance, I have, I don't know, 10 systems already in my collection, when I build the collection, this is where I'm deciding to say how large it has to be. I have 10 systems, then you can have differences like of 0.6. Saying the raw square, that measure that tells you how good your data set is, can be 0.1 or 0.7, can be 1 or 0.3. That's a huge difference, just depending on what systems you have. So basically this is saying you can't trust anything we say. And I'm saying this. In fact, you see that you need to go to at least 50 systems, already 50 systems, to have a smaller of maybe 0.1. Let's say that 0.1 is fine. You need 50 systems already to have that. That's a full collection already, right? So if you're building a new collection, you need actually as many systems as you can get to decide how large the collection can be. What about the number of topics or queries here instead of systems? So you're building more and more queries, more queries, more queries. Just, let's say you have 20 queries already, you can get differences of up 0.8. So that tells you your collection is just great or your collection is just BS. You have to add like 1,000 different queries to have a good collection, right? It just depends so much on your initial data. And again, magical number, if you go to 50, that's more or less what you need to have in order to, get your results like in the span of 0.1. That's already a full collection. So what this is saying is, our methods to decide how large a collection should be, you can't trust them unless your collection is already big enough by the current standards. So we are screwed, right? We have to build collections trusting these things that obviously we can't trust. No way. So, anyway, all this is based on a lot of assumptions. If we go through the ad hoc measures, then the problem is, what model do you use in your split half interpolation, right? Because you remember from before, those are huge differences, right? Which one do you trust? In terms of the statistical assumptions, oh yeah, we have normal distributions. But we have something called stochasticity. That means that all the systems have the same variance. We don't have correlated effects. All our samples are truly random samples. Those assumptions just fall by definition. They're not true. We don't have Gaussian distributions. We don't have homoscedasticity. We don't have random sampling. Just by definition, we don't have them. And in fact, when it comes to measuring variance, we're terribly bad at estimating the variance. And that's the problem here. We are terribly bad at estimating the variance of the systems. We don't know how to do that. And so those things are false by definition. And this is like the foundational background from all these ways of measuring stuff. So just as an example, here's a system. This is reciprocal rank, and that's supposed to be Gaussian. And here we have topics, we have a system, and we see a clear correlation there, right? We have one system, we have another system, and we have a clear correlation there. those things are supposed to be uncorrelated and Gaussian, and of course they are not. Right? So how much does all of this affect our scores? So in summary, we have this non-trivial machinery to address the reliability issue in information retrieval, recommender systems, machine learning, anything in which you have a data set and you crunch numbers on that data set. Right? So we have absolutely no idea how it works, and apparently it doesn't work very well. And so the problem is that all the related research is unfortunately limited by the data, because